All right. So, wait. Oh, fuck. Hello, hello. All right, bet. So, got the mic back on. I uh, I have 20 minutes to do this leak code review. Hopefully, I can get through it. If not, I'll just go probably more in depth with the other stuff. But today, I solved the clone graph problem, and let's see what I should review. Yeah. So, boop, boop. So, uh, roadmap. Backtracking. Permutations. Have I done permutations? Yeah. So we're almost done with the leak code. Hmm. So we're almost done with the questions that I haven't I I haven't made notes for. And then once I get to the questions where I did start taking little notes, I think the reviews will be a lot easier to get through because I can remind myself of different little things that happened. So permutations, I'll probably just go over it conceptually and do the code when I have a little bit more time. But it says, given an array, nums of unique integers, return all possible permutations. You may return the answer in any order. And I did this August 23rd, so a little while ago. Answer in any order. So we only have unique integers. Permutations are defined as, let's see, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3. Okay, so it's just the different orders that you can place these unique values. There won't be any duplicates, so there won't be any weird cloning um, logic or whatever, or like weird branching logic. Because I realized that with duplicates, you have to think of some base cases where you have to cut the branch off shortly or sort the branch and um, iterate through it as needed so that you can not waste times doing recursive calls that you have already did. But understanding the problem, we're still trying to do umpire because byte size is wise and they recommended it. You may return the answer in any order. So um, when they say you return the answer in any order, it probably doesn't mean that like these can be whatever they can. Like the order of the subarrays matter is just like how the subarrays are ordered inside this main array is organized. That does not make sense. Fuck. The subarrays, the order matters. In the global array, where the answer array I usually call it, the order does not matter because the order of that is probably just determined based off of how you choose to do the recursive branching. So let's get into it. Permutations are just different ways you can organize your numbers in here. I might be thinking of an overcomplicated solution right now, but let's get into the planning of it. So umpire is understanding. What is M in umpire? Fucking umpire solving method. It's my third time Googling, fourth time maybe. So U is understanding, M is matching. Okay, so something recursion, right? So probably depth first search because anything where you have to find a bunch of combinations of something, recursion works best. And then probably thinking depth first search. Well, I probably should be more knowledgeable on when to use depth first search versus breadth first search. I think depth first search for this is great because you can get your first subarray first, and from that subarray, once you backtrack, you can change one thing, and from that you backtrack and change another thing, and you keep doing that until you get all the subarrays that you need. Planning. So planning is what I was trying to rush towards. Let's get to Excalidraw and get it going. Let's get it going. Got 15 minutes. All right, Excalidreezy. That was cringe. Okay. Let me sit up. Okay, so we have this thing here. Let's copy that. Put it in as text. Make that a little bit bigger. Alright, that's really too big. So we know that we have to iterate through our input array somehow. We don't have to do it through our recursive calling, but we do need some way to iterate through 1, 2, 3. I don't think it's smart to do it through the recursive calling, because when you do backtracking, you have to properly change your index. Well, I think it's not that bad actually. We can do it through that. I think we will actually. I'm being stupid. So we're gonna start with nothing in our base case, right? We're gonna start with an empty array, and this will be when our def first search is called. Oh wow, this is slow right now. Our def first search for call with some type of base case is gonna start with an empty array. So instead of a 0, it'll probably just be an empty array. And from there, we can, and we probably need some index if we're gonna track it through here. And that index will tell us where we are looking at on this array. We know that is unique, so we don't have to worry about duplicates, but we now need to worry how to reach these different subarrays once we hit each branch. So in the first one, obvious solution would be to append 1 first. So we're at index 1, and then once we append 1, we go ahead and append 2, and then again at 3, append 3, 1, 2, 3, right? And then from each of these, the index will just increase by 1 until it reaches the end. So we know that one of our base cases is once our index reaches the length of this nums, meaning that once I equals 3, we can break. So that's our base case. One of them for so far. When I equals 3, I equals the len. I gotta make this bigger, bruh. Jeez Louise. When I equals len of nums, then we break. I'll just leave it like that for now. Holy shit. What the hell, man? I'm gonna leave it. Whatever. That's the base case. And then now we got to figure out once we do a backtracking, right? So we hit our base case. We know that once we get one of these, we append it at the global array. So blue, we had to append when I circle blue to app. I don't know why Excalidraw is real slow. I think it's because I'm zoomed out a lot actually. So now I know. Now that, so we append this and now we're backtracking, right? So we need to adjust this back to where it gets back to 1, 2. So when after our append or our first recursive case, if we want to do another recursive case, we need to pop this 3 out of it, right? So some pop on the way up, or some readjusting of values so that we are reset as needed. And then, so what can we do from here? So now we have 1, 2. That's one of our permutations. And then once we have 1, 2, that's one of our permutations. And then, well, we already visited 3, so there really isn't any other options, right? So I'm guessing the index, if you have already visited it, we don't change this index then, right? This I, we don't change. We only pop off the 3. And the reason for that is, even though since index is right here, let's say this nums array had a 4 instead. Instead of doing 4, we can do 1, 2, 1, 2, 4. Wait, that doesn't make sense actually. How did I do this? Let me think. Oh, I think I didn't solve this with a traditional recursive tree actually. I did it differently. I think I remember how I solved this now. I was struggling with this same problem, and instead of solving it by drawing out a tree like I usually do and trying to fine tune the little details, I think what I ended up doing was I started with an empty thing, and then we are still iterating through it, right? I'm just using a different visual representation of this tree, and pretty much what we do is we append 1, right? we append 1, and the difference is when we get to 2, we have options where we put the 2. We can either put the 2 before the 1 or after the 1. So that gives us 2 options. We can have 2 1 or 1 2, right? So we're gonna need some for loop that has a line through it right here. So this is what I visualized when I was solving it. I remember it now. We need some for loop, and then once, if our line is here, we know that we append before the line. So if it's here, we append at in the front. If it's here, we append after 2, and then once it reaches outside bounds, then we know we're good with our appending. So that's how I visualize how to add those, and this will work no matter how big the array is. You just need to make sure you set your bounds correctly so it doesn't throw an error. And then the last recursive call will be, let's do it in purple. So now our index is done with 2 and now it's at 3, right? And so once, how do I move this? Oopsie. Once we are at 3, we know that we have a couple spaces. We have more than 2 spaces to go. We can either go before the 2, in the middle, or after. And this is for both cases, right? Because both will give us different permutations. And so this way we can have 3 options for each tree. And 3 options will be 3 2 1, 2 3 1, or 2 1 3, right? And then this is going to be, since I has reached the end of this array, we know that we already have the shit that we need, right? And then we're going to do the same thing here. So here would be 3 1 2, and then 1 3 2, and then 1 2 3, and then that would be our 3 that we need to append. Now we have 6 subarrays that we have appended to our answer array or our output array, and then we can append that. And so the organization in which I did it is wrong, but is different from this example output, but the order does not matter, right? As long as our subarrays are identical to what is needed, right? So I think I just flipped these two. That's the only difference. So they probably appended from the right to the left, and I did from the left to the right, but either way works. And so let's talk about big O. Big O is going to be shit, I suck at big O. So the time complexity is going to be, since we have 3 here and we have 6 here, I'm assuming it's 2. Doesn't make sense, actually. How would you derive big O from this shit? I'm blanking. Someone help me. Shit. Well, so at every recursive call, let's try to break this down. At every recursive call, we know that the len, if the len is 0, right, we have 0 recursive calls. If the len is 1, we have 2. If the len is 2, oh shit. If the len is 2, then we have 3 each. So there's always one more than the length of the list. But then it breaks up into these branches. So every branch gives us like more and more. So this gives us 3 branches. This gives us 1 branch. 6 branches versus 2 branches. Honestly, bro, I'm low-key blinking. So I think that's a good thing with the review. Permutations. How did we derive big O, and how to explain it very nicely. And yeah, and then I also want to know best ways to approach recursive problems, because I usually approach it by building a tree and fine-tuning the conditions slash cases. This was visualized in a simpler way, but not in a way I'm used to, right? And so I got to work on that. But also, what was I gonna say? Shit, I got 4 minutes. Damn, that shit flies. What else what else can I learn from this? So I know from this question, I need to kind of break away from my traditional structure of trying to figure it out from the tree. It's very helpful, especially for the easy questions, but something like this simplifies it in a way that helped me a lot. I just wouldn't have been able to perceive it until I did this question. So that would be useful to figure it out. I know recursion in general, it's just breaking it down into the most simple examples, right? So I think instead of trying to build a visual of it first, I need to define the simplest version of a recursive problem and then build the visual. Maybe that would be helpful, but we'll see. Keep practicing and we'll find out. I'm gonna end it here. I'm gonna start my meeting, and hopefully the next one will be a little bit